Greetings and welcome to the introduction to astronomy. In this lecture, we are going to begin our discussion of Earth and talk about its interior structure. So what does our Earth look like inside? Well, let's get started and we'll look first of all, let's look at the basic properties. Here is our Earth from looking at the surface of Earth, and we see that it is covered with water, about 3/4 of Earth's surface, and the rest would be land. So we can see those areas. We see lots of clouds around and various different structures within it. And we're going to look at that in more detail over the coming slides and lectures. Now, basic properties are that the Earth is about 12,756 kilometers in diameter. It has a mass of nearly 6 times 10 to the 24th kilograms. Now, often with these numbers, what we tend to refer to is we compare other things to Earth. So we would consider this one Earth mass. So we would write that as one mass and this circle with the plus through it for a mass of the Earth. This would be, we'd use the radius of the Earth. The diameter would be twice that. We would say about 6,000 kilometers is one Earth radius. And we can use that to be able to compare to other planets more easily than using the very large numbers that we see here. Now, the density of about 5.5 grams per cubic centimeter means that Earth is made up of a mixture of metal and rock. Its rotational period 23 hours and 56 minutes, and recall that is the sidereal rotation period, how long it actually takes Earth to rotate. Our day is 24 hours based on the sun. And it has an escape velocity of 11 kilometers per second. So without an atmosphere, if you could send something up at 11.2 kilometers per second, it would be able to escape from Earth's gravitational well and head out into interplanetary space. That does not mean, again, it escapes Earth's gravity. Gravity would always pull on it. So let's look what is unusual about Earth. We start our discussion of the solar system with Earth, but Earth is actually very unique in many ways. It is the only planet with liquid water currently on its surface. It is the only planet with oxygen in its atmosphere, and the only planet known to have life. So it is unique in many ways compared to the other planets. We will not see liquid water on the surface currently of any other planet, although it is likely that we know that Mars likely had water in the past, and possibly even Venus in its early history before it became too hot. Oxygen is a very reactive element and doesn't last very long. So it takes life to keep that in its atmosphere. And we are again the only planet known to have life. Now let's look at the interior of Earth, and we can look at this cutaway here. The inner core is a solid portion that is iron and nickel. The outer core is molten, but is also iron and nickel, along with a few other lighter elements. So once you get to this inner portion of Earth, pretty much all of this is solid metal, solid or liquid metal, I should say. So it's pretty much all iron and nickel, some of the more common metallic elements that exist. Now, the mantle is kind of in a molten or semi-molten state, depending on the pressure. And we see that as a very rocky material. We're done with the metals now, but have a much more rocky material here. And then we get to the crust, the surface layer, where the lightest materials are. What do we find out? Those are very light rocks. And we also find the atmosphere and the water there. Again, things that are very low density rise to the surface. Now, how do we know this? We can't drill down there. In fact, let's look. Can we drill to the center of the Earth? No, we can't even get close. Our deepest drilling is about 7 miles. The distance to the core is about 4,000 miles. We've given about 0.2% of the way to the core. We need indirect observations. We need to use other things that we can use to interpret this. And one of the things that we look at are earthquake waves. So when an earthquake occurs at one location on Earth, those waves travel through, and we see different waves will travel through, and they will bend at different areas depending on the densities. So through the crust and the upper mantle, the lower mantle, and into the cores, they will be able to travel, and that will give us again an idea of what kind of waves are we're seeing. And using the information from not just one earthquake, but from hundreds and hundreds of earthquakes that occur around Earth all the time, we can put together a model of the interior, how it has to be inside in order for those earthquakes to travel through there. For example, we have certain types of waves that cannot travel through the interior. So certain waves cannot travel through liquids and they will not get to the other side. And that tells us about the liquid portion of the of the crust and the core. So we can learn that by looking at all of these earthquake waves, even though we cannot come close to getting down toward the core of Earth. Now, what do we get from some of this? Well, we also want to look at Earth's magnetic field. And how do we look at this? Well, this is outside Earth's core, but it actually is generated by electrical currents in the outer core. When you have a moving electrical field, you will create a magnetic field, and electrical currents within that liquid metal in the core will then generate a magnetic field around Earth. And while Earth's magnetic field is not strong compared to what we'll see in the outer solar system or for our own sun, it is the strongest of the terrestrial planets. So we have the magnetic field extending out beyond our atmosphere into what we call the magnetosphere. So that is where Earth's magnetic field is dominant. And that is very important for us because it protects us from many charged particles from the sun. These particles then cannot penetrate through the magnetic field and they get bounced away by it perhaps. Or some cases they come around it and they funnel in toward the poles. So this is where we're going to get the aurora near the north and south celestial poles, because north and south magnetic poles, because of where they happen to get the particles in. But it protects us from this bombardment of solar wind particles and other cosmic rays from space. Now, not all of them get deviated into the atmosphere or away from Earth altogether. Some of them become trapped, and that gives us the radiation belts that we see here. And those are the Van Allen belts that are present. Those are collections of particles, high energy particles that are trapped in belts around the Earth. They're not pleasant places to stay. You would not want to linger in one long. But as was shown with the Apollo missions, astronauts can pass through them, and we're going through them relatively quickly. The radiation exposure is minimal. However, there are not places you would want to place a satellite or a space station or anything because of the much higher levels of radiation. So let's go ahead and finish up with our summary. And we looked at the interior of Earth and looked at how Earth is a unique planet in many ways. We learned how we can map the interior structure of Earth using seismic waves. And we found the crust, the mantle, and then the outer and inner cores. And we also looked at how the liquid portion of the outer core generates Earth's magnetic field, which helps protect us from charged particles from space. So that concludes this lecture on Earth's interior structure of the Earth. We'll be back again next time for another topic in astronomy. So until then, have a great day, everyone, and I will see you in class.